Thank you for letting me speak. I'm Alex Quent. I am a fourth-year PhD student now, so nearing the end, with Wilkinson. And my topic today will be also about Bayesian statistics of success, but about power in between subject designs, or the context of between subject experiments, and how Bayesian sequential designs might be helpful in this context. So the outset of the problem really is that concerning the actual facts that we are likely to encounter as researchers, or that we might chase after, and the sample size that we typically run are not really well matched. So in other words, our field still does run a lot of underpowered studies. And that is even more true for between subject designs, and probably even much more of a problem in fields where data collection is expensive, such as imaging, or also other kind of experiments. So that basically means we still have a significant power issue. So, I think this paper from 2019 from Mark Brisbane makes a really good and convincing point. It's quite long, but I think like even if you read like the first half of it, I think you really get the point really easily. So like I definitely encourage you to skim it at least. But just to really like show you what I mean by this is so for a normal frequentist unpaired t-test between subjects t-test, in order to get a 80% chance of finding a significant p-value for a medium effect size, you need 63 participants and 126 participants in total. You need even more, obviously, if the effect size is smaller. So 0.5, you already need 95 participants per group, or 175 if you have an even smaller effect size. And that's an issue, and we can basically probably, I mean, some people do run these kind of experiments, but how often do we still come across studies that we read that do between subject designs that are nowhere near the numbers that are actually needed to find, that are nowhere near to have enough power. Things are actually a bit worse at least at the first glance with Bayesian statistics. So if I run the same unpaired equivalent in a Bayesian t-test, I have to collect 110 participants to give an 80% chance to detect a medium effect and get a base factor over 6 for this. But as you'll see in a second, Bayesian statistics allow you to do something that you're not able to do in frequency statistics, without having some sort of correction in this, and that is even leads us to Bayesian sequential designs. So the one, just building upon what Frank just explained. So within the Bayes theorem that you see here on the slide, you can calculate the base factor, which is in principle a ratio between two competing hypotheses with which you can express the evidence in favor, for instance, of an alternative hypothesis and a null hypothesis, very similar to the null hypothesis testing framework. And the good thing about this is basically it allows you, and it's like it's a bit beyond the scope of of my talk here, but at the end I do have like some slides of why it is possible. But the only important thing is here we can look at the data after each data point without having to test for multiple comparison or to do any other kind of adjustment, which and then do optional stopping, which is not possible with frequentist statistics in that way. So what are sequential between subject designs? So in a between subject design, I just show you the algorithm that's necessary to the data collection algorithm. So you basically start with a minimum sample size of, let's say, 10 participants per group. You run your base factor analysis, and then you check, is my base factor above 10, about 6? If it is, you're happy and you can write up and you submit your paper. If it's not, then you check, maybe my base factor is below 1/6. In that case, that would mean we have actually relatively strong evidence that the null hypothesis is true. If that's the case, you also stop your data collection and you write up your paper. Or if it's not, you basically increase your N until you reach either of the two criterions. Obviously, this kind of approach has to be paired with a pre-registration, or to be contacted, for instance, registered report as an even stronger form of pre-registration. But this is a perfectly valid way of like collecting your data. And that is very efficient in terms of like how many participants we need. But it's not compromising the ability, it's not compromising power in the same way of just running an experiment on just 20 participants per group. However, one shortcoming of this algorithm as it's on the screen currently is that on average, it is quite efficient, and you probably can stop your data collection quite early with a relatively decent number of participants, not excessively high, but occasionally, as you'll see in simulations, you do end up having to collect hundreds, if not 1,000 participants to actually converge on either of the two criterions. So therefore, it's kind of prudent to set an upper limit to what you'll be willing and able to collect. And that can be constrained in terms of grant money, time of your contract, time it takes to get your degree. So these can always be valid reasons to say, oh, I'm only able to collect 90 or 100 participants per group. And this still allows you to get a quite good performance of this data collection algorithm, as I call it. So if you're interested how this works, so here's basically, well, basically the same information than in the previous slide, is a sample code which allows you to simulate one iteration of this, or simulating this one algorithm one time, where you continue to collect data until you've reached a criterion. And this will be uploaded probably by the end of today into my Bayesian Sequential GitHub repository. And I also have the actual simulation script that I will show you in a second, where I run a full-fledged simulation of how basically a power analysis, like how this algorithm performs for various effect sizes. So to see how this algorithm actually works in terms of power, we can run the algorithm, this data collection algorithm, 100 times and see how often do we get a base factor of 6 and at which sample size, basically. And that's animated here in this GIF, where each line represents one experimenter basically collecting their data until they have reached a criterion. And you can, if you do this 10,000 times, you can create a graphic like this. And that's basically in the middle of the same thing. So each individual line represents one experiment, one fictive experiment where data is collected either until we reach a criterion, for instance, a base factor of 6, and then we leave it from the to the top. And the histogram basically show you the relative. So the heights of the histogram show you how often do we end at a particular sample size, or we leave at the bottom, which will be evidence for the null hypothesis. And you see, also example, in this case, if we have a medium true effect size, this only rarely happens that we get strong evidence for the null hypothesis. And if we basically reach our maximum, and in this simulation, it's set to a maximum sample size of 95 participants per group, then we also have a number of like what we would call undecided base factors, and you see basically due to the color coding, you see how they're distributed, and this can be useful basically to guide the decision. So if we compare how this performs in comparison to a frequentist way, so with this sequential base factor analysis, we have an average sample size of 56 participants. And this is compared to a 63 sample size that you must collect if you want to be adequately powered with a frequentist t-test. But we have, in both cases, we have the same power. We have 80% chances. But just also keep in mind that is despite the fact that there are huge differences in terms of like what bar of evidence you need to reach to get a base factor of above 6 compared to a p-value compared to 0.05. And something that you obviously can't do with traditional unpaired t-test is we get evidence for the null hypothesis as well. In this particular design, for instance, with an average sample size of 91 participants per group, we get at least strong evidence for the null hypothesis in still 32% of the cases, which is not overwhelming, but specifically in between subject designs, you need to have a lot of participants to really to get your number much higher than that, because you basically see that before a sample size of 80 something, it's mathematically impossible to get evidence for the null hypothesis, just basically the way that that is calculated. So only after then it starts giving you evidence for the null hypothesis. I basically now want to end with my conclusion, and hopefully I gave you see this as a small teaser of how a Bayesian sequential designs can be a useful tool to provide strong evidence while saving resources. And specifically, on the note of resources, obviously, we have to be willing to also spend at least some money. So we need to stop running these small, inadequately powered studies, because obviously it's cheaper to run an experiment just on 20 participants per group. But as a society and as a community of research, we are basically losing money because we are all chasing so much noise, trying to replicate other experiments. And I don't know how often you felt that, if you're kind of doing a literature review and you're trying to find out, okay, what a true effect, what are not true effect, and some things are just so confusing. And the reason, apart from that, one of the reasons, as that obviously similar to what Johan explained a couple of weeks ago, is that a lot of these studies are just inadequately powered, and we are chasing effects that are not really there. Then obviously, one thing that we need to be cautious of, or what the limits of Bayesian sequential designs is. The first one, as you probably also saw, they are more conservative than frequentist statistics, which is by some regarded as more of a feature than a flaw. And also things become a bit hairy if you have more than one hypothesis you're interested in a given design. And this probably might be true, especially in an imaging context where data collection is also quite expensive, then you want to get as much of this as possible. But basically what you can do, if that is the case, then probably one of the suggestions is starting with a minimum sample size that will still give you some indication or some ability to say something about a hypothesis regardless of when you stop. And then basically just use this data collection algorithm. And obviously, one other thing is that's illustrated with this additional animation is, in contrast to in the frequentist realm, we have to have priors of some sort for Bayesian statistics, and Bayesian statistics, especially the base factors, are quite sensitive of how, for instance, how wide your priors are, and that's basically illustrated with this, where you see just quick. If hopefully that's visible enough, but you see the effect size on the x-axis, basically the power, the percentage of cases you reach a certain criterion, and you get support for the alternative hypothesis, that is the dotted or dashed line, and solid lines would be support for the null hypothesis. And you see how and the colors are the different priors, and you see how they are influenced by each other, and also by increasing the sample size, obviously. And yeah, as I said, this talk is more meant to be a teaser than an exhaustive, than specifically telling you everything that you need to know to run these kind of things. Therefore, I have a couple of pointers for you at the end of the slide, and also obviously my mailbox is open for you to ask me questions. And I think now you hopefully this gives some people the idea of like using these kinds of methods. And yeah, I thank you and my lab, obviously. And now you can share the pain because like they have to listen to this quite often.
Thank you, Alex.